Thank you. So first, it's a great pleasure being here in Marseille. So it's always a pleasure being at CM. So I want to thank the organizers for their kind invitation to this meeting. And I want to apologize to the speakers of the first 2 days because I missed these days. I'm going to miss the day of tomorrow because I have to leave to return to Paris. So I'm very sorry for that. And so without further apologies, let me mention that it's the work I'm about to present is a paper written with Claude Bardos from Paris and Ivan Moyano, currently in Cambridge. So so linear Boltzmann equation and fractional diffusion. Let me first start with a few remarks on how diffusion equations, fractional or not, can be derived from linear Boltzmann equation. And so perhaps you've seen some of that stuff in the talk by Ludovic Cesbron, but there are certain features of this approximation which I wish to recall because they're going to be used later in the talk. So the most elementary way of deriving a diffusion equation from the linear Boltzmann equation is to start from a linear Boltzmann equation for a system of monokinetic particles. Monokinetic meaning that these particles, they have speed 1, they have the same speed. And so the velocity vector for the particle is just a unit vector, omega, on the unit sphere. And you write the linear Boltzmann equation where the unknown is the distribution function f for t, x, and omega, a non-negative function, that's the probability density of having a particle at the position x moving in the direction omega time t. So here, this linear Boltzmann equation tells you it governs the evolution of this distribution function f. And here, so you have the free streaming operator. So you have some scattering rate sigma, which in the left-hand side of the equation governs it explains, it tells you the rate at which particles are deviated or the direction is modified by collisions with the background medium. And on the right-hand side, you have a scattering operator, which here I've taken to be the simplest of all, the simplest imaginable scattering operator, meaning in this case, the isotropic scattering. So here I just take the average of f in angle in the direction omega prime, right? So here this average I will later on denote with brackets like this. And so you see immediately that in the regime where the scattering rate sigma is large, so here sigma for all practical purpose, we can take it to be equal to a constant. So if that constant is large, you can expand the distribution function in powers of 1 over sigma. If you do that, you see immediately, and that's an equality, that in fact, the equation you can write in this bizarre way, right? So f, t, x, and v to leading order, it's average, it's angle average, plus a perturbation of order 1 over sigma, which involves the omega grad x of f and the time derivative. And if you further approximate, so to leading order, you see that f is going to be close to its average in angle. So it should be an omega and not a v, sorry about that. So if you further substitute this approximation for f under the derivatives, which is, of course, highly questionable, but suppose that you do it no matter what, right? So then you see that you have an expansion for f of tx and omega. To leading order, you have an isotropic function. Then you have a linear function which involves the gradient of the density, the macroscopic density. So this is a correction because it was a 1 over sigma factor in front, and there is the time derivative, and then terms for the 1 over sigma, which are small compared to 1 over sigma, right? Okay, and then from then, if you want to derive the diffusion equation, you use 2 fundamental ingredients. First, the local conservation of particle number, which is an exact identity, which is that d by dt of the average of f in omega, plus the divergence of omega f, the flux, this is identically equal to 0. This you see by returning to the equation here and averaging both sides of this equation in omega, right? And this you get immediately this relation. And the item B is to derive the Fourier law for the current. So in other words, you want to be able to say that the omega f, approximately the average of omega f, has to be proportional to the gradient of f, right? And this you see by returning to this formula, to this approximate formula for f, and you see that if you compute the current, omega f, and if you average, the first term here is going to go away, and so this is the computation that you see here, and you see that the omega f to leading order is going to be proportional to the gradient of the macroscopic density. And if you do the computations, you see immediately that the average of omega times omega is proportional to the identity by isotropy. And here you have that the diffusion coefficient is 1 over the space dimension times sigma. And then you have the gradient of f. And therefore, from this, if you plug this information here, you see that there's a minus which is missing here. I'm sorry about that. There's a minus, which there's a typo. There's a minus, and you see immediately that d by dt of rho, so rho being the limit as 1 over sigma tends to 0 of the average of f. So the rho approximately is going to solve this heat equation here. But there's one interesting feature. So here it's an argument which is, of course, kind of formal, which can be made rigorous. Let me say a few words about the boundary conditions, right? Usually the linear Boltzmann equation comes with a boundary condition that could be, for instance, that you prescribe the Dirichlet condition for the density of incoming particles entering the domain. So if the linear Boltzmann equation is posed on a C1 domain omega with outward unit normal that you denote by n, and it would be natural to prescribe the Dirichlet condition for incoming particles, so f of tx and omega for omega dot nx negative, so for omega entering the domain. So if you prescribe this to be equal to a given density that you choose to be isotropic, independent of omega, right, Rb of x, then in that case, to leading order, not surprisingly, you will see that the boundary condition for this diffusion equation here is going to be the Dirichlet condition rho equals Rb on the boundary. But if you go to the next order in 1 over sigma, then in fact, you can prove that the next order for the boundary condition would be a Robin boundary condition, meaning something that involves not only rho, but also the normal derivative at the boundary. And this is a correction, so not surprisingly, it has a 1 over sigma factor in front. And there is a coefficient here, L, which goes by the name of extrapolation coefficient in transport theory. And in the case of space dimension 3, and for isotropic scattering, you can compute it, and it's 0.7104. Right, so it's a solution of the Milnor problem computed by Chandrasekhar. It's been known for a long time. I mean, it's not fresh science, you know. It's old stuff, right? So anyway, so here you see that you replace this boundary condition here by this one, which essentially is equivalent to saying that the reason why it's called extrapolation length is that this is essentially equivalent to saying that you have a Dirichlet condition on a domain which is slightly larger. So you enlarge the domain omega by a length which is precisely L over sigma, which is small, and there you have the Dirichlet condition. Okay, so we are going to recover this Robin boundary condition later in the talk. Okay, so. All right, now, in the case, so there are several ways by which fractional diffusion equations can be derived from linear Boltzmann equation. One first approach, I think, is the one I learned. I learned from a paper by Antoine Mellet, which I think is in the Indiana University Math Journal, maybe 2009 or something. And so here you start from a linear Boltzmann equation about the same form as before, except that here you have an equilibrium which is not simply constant, right? You have an equilibrium which involves a probability density in Rd, which decays algebraically for large values of V. Okay, and so it decays algebraically, and typically it's like the length of V to the minus D minus 2 alpha, where alpha is between 0 and 1. And what Antoine proves is in the limit, as the scattering rate sigma goes to infinity, then F is going to look like a function of T and X. Well, more precisely, it's going to be a function of T over sigma to the 2 alpha. So in other words, the appropriate time scale to describe the large sigma limit of F is T over sigma to the 2 alpha, right? And times M of V. And the rho, this rho profile is a solution to this fractional diffusion equation with some coefficient C, which you compute from the data, right? So here, if you would apply if you would try to apply the argument which I showed you before, it would not work, because it would be the fusion coefficient that you would try to compute in this way would be the second moment of this Maxwellian here, and the second moment turns out to be infinite. So that's one of the reasons why the standard diffusion doesn't work. So in other words, here the standard diffusion does not apply because of the fat tails, the heavy tails of the distribution, the equilibrium distribution at infinity, right? So there is another much older, I think, way of obtaining fractional diffusion from a linear Boltzmann equation, which I found in a paper by Hélène and Uriel Frisch. So MNRAS, it's monthly notices of the Royal Astronomical Society. So it's really a paper about, it's really a paper in the astronomic community, right? It's not a math paper. Nevertheless, it has very serious mathematical content, right? So their starting point was non-LTE, meaning local thermodynamical equilibrium radiative transfer. So it's a kinetic equation for photons. And so here, I of x, mu, and nu is the equivalent of the distribution function considered before. Here it's a steady problem. There's no time variable. And so you have sigma of nu, which is a scattering rate which depends on the frequency. So here the scattering rate goes by the name of opacity in this context. So it's a function of nu. And so here's the radiative transfer equation as you see it in the book by Chandrasekhar, for instance. So here you have a streaming operator. So you have the absorption due to the scattering. And you have in the right-hand side a source function times the scattering rate sigma of nu, and the source function is 1 minus epsilon times the scattering, the source of radiation that comes from the scattering, and epsilon times an external source that comes from the background, and which you choose to be isotropic. Typically in radiative transfer, Q of x would be a Stefan-Boltzmann law. I mean, something that is proportional to the fourth power of the temperature and depends on x only, right? So, and here for non-LTE radiative transfer, they consider a case where sigma has Gaussian decay. You see immediately that for large frequencies, then the damping effect of the scattering rate will disappear, will vanish very rapidly. And for that reason, the mean square displacement of the photons between two scattering events is not proportional to the square root of time, so you don't have a standard diffusion. And as a result, the appropriate scaling as epsilon tends to 0 for this equation here is to pick h epsilon to be this epsilon square root of the log of 1 over epsilon. And you see immediately because of that choice, I mean, this is the appropriate choice for analyzing this equation here. And you see immediately that it's a setting where it's going to be virtually impossible to use any asymptotic expansion method, right? Because you don't have a power law here, right? But nevertheless, if you look at the source function here, you can prove by some integral equation method that this S satisfies a fractional diffusion equation here. Possibly, I don't know, this is a different mechanism than the one in the paper by Melee, right? It's not a heavy tail business, it's more like the scattering rate vanishes at high frequencies. I'm not sure this is the same thing, right? Okay, so, right, I mean, I summarize on this slide what's going on in these two papers. So first, in the work of Melee, it's the fractional diffusion is produced by the heavy tails in the equilibrium distribution. And whereas in the work of Hélène and Uriel, Frisch, the scattering rate, the fact that the scattering rate is not uniformly large in nu, is responsible for these fractional diffusion. So in other words, you have a sort of a competition between the fact that for high frequencies, this equation here, for high frequencies, essentially you kill the scattering phenomenon. So essentially you have pure ballistic motion, whereas for low frequencies you have something that looks like a standard diffusion, that would look like a standard diffusion. So somehow the fractional diffusion here is a sort of compromise between the ballistic motion for high frequencies and the pure diffusion, the standard diffusion for low frequencies. So yeah, I mean, that's the best explanation I can offer at the moment. Okay, so let me show you still a third way of obtaining fractional diffusion from the linear Boltzmann equation. So for this, I'm going to, I mean, this is a way of obtaining fractional diffusion from the Boltzmann equation, from the linear Boltzmann equation, that's based on the harmonic extension approach. Right? So you have this Caffarelli-Silvestre lemma, which tells you that, which you probably know better than I do, which is that if you take function f in, say, LP of the torus, then you can represent fractional powers of the Laplacian of f as normal derivative of some harmonic, between quotes, extension of f, which would be really the harmonic extension in the case where you want gamma to be equal to 1. So if you want the square root of the Laplacian, it would be the real harmonic extension. And if not, it involves this, operator here, where you have an elliptic operator, but with some function of the distance to the boundary, right, which is y here. So you solve for that, you solve for f, that equation here, and with a Dirichlet boundary condition, which is f, and then the normal derivative is going to give you up to some constant. Well, I mean, the constant you can put it in the equation by some scaling, right, if you prefer. So if you put the constant here, then I suppose the normal derivative, I mean, which is the thing which is computed here, will be exactly the fractional power of the Laplacian of f, which you want to compute. And the constant depends on the exponent gamma in this way, right? It involves the gamma function. So you can check here that if little gamma is equal to 1, then the constant is equal to 1. This is the case which I shall be using shortly. So yeah, so in this case, so the fractional Laplacian appears as a Dirichlet to Neumann operator, but we shall see that this is not always true. I mean, the fractional Laplacian is equal to the Dirichlet to Neumann. I mean, the Dirichlet to Neumann operator is something that you can define in a very general setting. It's not always a fractional Laplacian, right? So we shall see that later, right? So there are examples where you can see. Of course, I mean, at high frequencies, always behave like a fractional Laplacian, but it's not equal to that, right, in general. Okay. Good. So then, so we want to be using this representation of the fractional Laplacian, and so we want to sort of mix that with linear Boltzmann equation in some way. Okay, so now I'm going to look at radiative transfer in a half space, And the position variable here is z, it's the pair x, y, so x is going to be on R2, y positive. And I'm going to consider the case where a scattering event does not depend on the frequency, so that I have a gray average over frequency radiative intensity in the direction omega, which is a unit vector in S2, which I denote by f of z and omega, non-negative. And the radiative transfer equation is written here. So omega grad z of f of z omega is equal to sigma times the integral of some scattering phase, p of omega scattering transition function, p of omega omega prime, f z omega prime minus f z omega d omega prime. And so you have this scattering rate, which is constant, frequency independent. It's a Thomson type scattering for free electrons. And you have the scattering transition probability p omega omega prime, which you choose to be a function which is L2 in omega omega prime, which is symmetric, everywhere positive, integrates to 1 in any of the variables omega or omega prime, and you choose it to be isotropic, meaning sort of equivariant under the action of the orthogonal group. So P of Q omega prime is equal to P omega omega prime for all orthogonal matrices and all omega prime. So there are numerous examples of such phase functions, so such transition probabilities for scattering events in radiative transfer. Of course, you have P of omega prime, which is equal to 1 over 4 pi, so it's isotropic scattering. So here you just have the average of f in omega prime. But you have more serious examples. For instance, you have the one that's called the Rayleigh phase function, which is 3 over 16 pi, 1 plus the cosine of omega prime to the square. And you have many others, right? So you can enrich your class of examples by adding polarization. So you can, well, so anyway, so these are just the first examples of such scattering transition probabilities. Okay, so this is so much for the equation. Now for the boundary condition, I'm going to assume that the incoming radiation, so the boundary is y equals 0, right? So at y equals 0, I'm going to assume that I have Lambert reflection plus an isotropic source, for instance, given by black body radiation. So what that means that f of x and omega, so for y equals 0, and for omega y positive, so this is the sum of this isotropic source term r of x plus this Lambert reflection law. So the Lambert reflection law, what it means is that you take the flux of photons impinging on the boundary and they're reflected isotropically in such a way that if it would be the pure Lambert reflection law, in such a way that you preserve the number of photons, right? So if you do that, then you will have the 1 over pi here. And here what I'm saying is that it's not pure reflection law. You have some coefficient, some albedo coefficient, which is something between 0 and 1, some alpha, and you have this additional source term, r of x, which is, for instance, proportional to the temperature at the point x, to the surface, right, to the fourth power of the temperature. Good, so with this, now I can introduce the scaling assumptions I need in order to derive this fractional diffusion equation from this scaled Boltzmann equation. So I'm going to consider a high scattering regime everywhere in the domain. So here I remind you that the domain is this upper half space, right? So everywhere in this domain I'm going to have a high scattering regime. And so, you know, this assumption manifests itself by the fact that I choose sigma to be large. And I'm going to have on the boundary a high albedo regime, meaning that alpha is going to be very close to 1. And it's going to be close to 1 in this particular way, right? I'm going to say that 1 minus alpha is going to be equivalent to 1 over kappa sigma, where kappa is some constant. And you can think of 1 over sigma as being epsilon, right? So 1 over sigma is our small parameter, right? And for instance, you can realize this by taking alpha to be kappa sigma over 1 plus kappa sigma. and in which case it's going to be convenient to introduce the source term. Instead of considering this isotropic source R of x, it's going to be convenient for notation to consider S of x to be 1 plus kappa sigma R of x, right? And henceforth, I'm going to use this notation. So the bracket, the single bracket, will denote the average, the average over angle of a function. And this double bracket with a plus or minus denotes the average with the omega y plus or minus. So this is the flux, which is normalized. So that's these double brackets with plus or minus are expectations, right? So if you the double bracket plus or minus 1 is equal to 1, okay? Good, so now, so here is the geometry, right? So you have an interface, so you have on the upper half space, you have this high scattering material, and so rather opaque material, if you want, and below the interface you have a high albedo medium, typically something which is fairly transparent. And so the idea is that diffusion approximation, standard diffusion will take place in the high scattering domain. And we have to see that the Lambert reflection law on the interface will will be somehow equivalent to the fact that the radiation pressure on the interface is going to be governed by a fractional diffusion equation involving the square root of minus the Laplacian, right? So that's the, if you want, the physical interpretation that you want to have behind these, behind the result, the asymptotic limit that I'm looking for, right? Okay, so now with this, in this setting, we have the following rescaled equation, right? So you have omega grad z f of z and omega plus sigma f equals sigma times the scattering scattering production term at the position z. So this is for z in the half space, and on the boundary, at the boundary for z equals 0 and omega y positive, so for the incoming radiation, then you have f of x 0 omega, which is equal to s of x divided by 1 plus kappa sigma. So if you want, this is our r of x, plus the Lambert reflection term, which can be written in this way, involving this double bracket notation. It corresponds to the flux of outgoing photons. Now the fact is that if you look at this, boundary condition here, you see that for omega y positive, or should I have said this is for omega y positive only, right? So for omega y positive here, you see that f is isotropic, it's independent of omega. So that's information which you can encode by saying that for omega y positive, this you can reproduce by saying, because f is independent of omega, you can recast this information in the following form. You can say that f of x 0 and omega is equal to s of x minus 4 kappa sigma times the flux, the total flux of omega f at the position x and 0, right, for z equals 0. So in other words, instead of having this flux of outgoing particles, you can replace this guy, right? You can replace this term here, which has order 1 as sigma tends to infinity, because you have the ratio of kappa sigma to 1 plus kappa sigma. And you replace this by the total flux, right? But the total flux, the average of omega f is small because we are in the diffusion regime and f is close to be isotropic, right? So the total flux here, to make it order 1, you have to multiply it by sigma, right? And so this, you can check that this identity here is equivalent to this one, right? I mean, this is in principle simple arithmetics, unless I made a mistake. But I think this is correct, okay? So, I mean, essentially, you have to use the fact, as I said, that for positive omega y, this boundary condition tells you that f is isotropic in omega. And if you use this, you establish immediately this equivalent form of the boundary condition, okay? Good, so now here is what you can prove. So I'm going to call Z, yeah, I mean this capital Z or Z is the domain is the product of the two-dimensional torus. So I'm going to assume that on the, for simplicity, I'm going to assume that on the interface, my data is going to be periodic in both directions, right? So you have T2 times, so Y is between 0 plus infinity, Y is positive. Now I'm going to denote by L the linear Boltzmann operator. So here it's simply f of z on omega minus the scattering source term, which is computed in terms of f and the phase function. And so the result which we obtain is that if you assume that the source term here, this S of x, is a Lipschitz continuous on the torus, then first you can prove for each positive sigma there exists a unique solution to the boundary value problem, which is going to be uniformly bounded in L infinity of z and omega, right? So this F sigma is uniformly bounded in z and omega. And not only that, but the tangential derivatives are going to be also uniformly bounded as sigma tends to infinity in z and omega. And so if you want, this is the fact that the problem here, this boundary value problem is well posed and the solution is uniformly controlled in terms of sigma. Sigma tends to infinity. But then you want to understand what happens to this solution as sigma tends to infinity. And this in the limit as sigma tends to infinity, what you can prove is that if you look at the boundary value, the trace of f sigma on y equals 0 on the interface, so this is going to converge, this sequence of function is going to converge to some r of x, which is going to be a function of x only, although the convergence here is a weak convergence in L2 in x omega for that measure, which is the measure for the flux term, right, on the interface. And this r is going to be the solution to the fractional diffusion equation, which is written here. Right, so you have r of x plus some coefficient times minus Laplacian square root of r of x equal to s of x. Right? So the s, I remind you, is the source term which appears on the boundary condition here, and then the restriction of f to the boundary, if you want, the Dirichlet condition for f on the boundary, is obtained by solving this fractional diffusion equation. So here, the coefficient involves a capital omega function, and the way you obtain this capital omega is by solving this integral equation for capital omega. So the fact is that there exists a unique capital omega, which is L2 over the sphere, such that the linear Boltzmann equation applied to capital omega, component-wise, is going to be equal to little omega, and uniqueness is obtained by postulating that capital omega should be average 0. Of course, this L has all the constants as is null space, and therefore, if you don't add this condition here, then you have a one-dimensional set of solutions, right? Good, so, right, so you have a fractional diffusion equation here that is obtained by this diffusion limit, looking at the boundary. Right, so the fractional diffusion is established on the boundary only, and on the on the half space you have a standard diffusion equation. Good, so what's the strategy? Well, the strategy is fairly analogous to what you would do in the standard diffusion limit. Okay, so first you have to prove that because f sigma is uniformly bounded in L infinity, modulo extracting subsequences, it's going to converge weak star in L infinity in z and omega to some function rho, which is going to be a function of x only because of to leading order the Boltzmann collision integral will tell you that the limiting function, the limit of f sigma, has to be in the null space of the collision integral. And then the next thing is that the deviation, the fluctuation around the average in omega, you have to prove that this fluctuation times sigma is going to converge to minus capital omega grad z rho in L2, where I remind you that this capital omega is the function which you obtain in this way, right? So that's pretty much the same thing as in the standard diffusion approximation, right? So here you get almost for free rho is L infinity because it's a limit of a sequence bounded in L infinity, and grad rho is in L2 because you can show that this quantity here is bounded in L2, right? Once you have this, then you have to prove that the equation for rho, not surprisingly, rho is going to be harmonic in the upper half space. And you have to check that on the boundary, you have this Robin boundary condition, which, you know, if you think about the beginning of the talk, I told you that if in the standard diffusion equation to the next order in 1 over sigma, there is this normal derivative that appears as a correction to the Dirichlet boundary condition for the diffusion equation. So here it's a little bit of the same thing, with, however, one subtle difference, right? So it's a little bit of the same thing because if you look at the boundary condition here, written in this form, you see that I have f, which is equal to s on the boundary, except that f is equal to s plus something which involves the flux of f. But this thing that involves the flux of f, the flux of f is enhanced because it's multiplied by sigma, which is a large parameter, right? So in the standard diffusion regime, standard diffusion, if you have Dirichlet boundary condition on the boundary, this term involving something which is of order sigma times the flux does not appear, right? And the sigma times the flux, which appears here because this assumption that the albedo coefficient is close to 1, this is the thing which is responsible for the appearance of the fractional diffusion equation in the limit, right? So you have this guy which appears here. But if you remember also, I told you at the beginning that the Robin boundary condition, this, I told you at the beginning that the coefficient which appears here would involve some kind of boundary layer term, non-explicit. So here, none of that, right? I mean, here the coefficient which you get is something which is essentially explicit because it comes from solving this equation here, and in many cases it's totally explicit. So the fact is that because it's to first order, it's not this equation here that you have to solve, but it's an equation that also involves a streaming term, right? So there's a subtle difference here which needs to be noticed. But nevertheless, you know, I mean, it's a term of the same structure which you obtain, okay? And then, all right, then you have to prove, well, it's mathematical requirement that you have to prove that the trace on the boundary of f sigma converges to the trace, it converges to the trace of this guy, it converges to R of x, which is the trace of this guy, and that the flux of f converges to minus 1/3 of capital omega dot little omega dy rho on the boundary. And the convergence here is in h minus 1/2 of T2, right? So if you want to pass to the limit and obtain the fractional diffusion equation, you have to do this, right? So you have to do these two limits. Good. So maybe some key ideas in the proof, which I'm not going to do in detail. I mean, surprisingly, the proof even of theorem A is surprisingly messy. I thought it would be much simpler. I was very disappointed. I mean, there's some very unpleasant features in the proof, which I don't know exactly, we don't know exactly how to remove them. Anyway, so there's the first thing, at least, which is very easy, which is that the operator L, you can check it's bounded, self-adjoint, Fredholm on L2, and therefore you can check that the null space is one-dimensional. It's a set of constants. This is a consequence of the fact that the scattering transition probability is everywhere positive. Right, so the range is the set of functions that are mean zero functions, and you can check that you have this spectral gap for the collision operator. So if you take function phi, you integrate it against L of phi, where L is a linear collision integral, and this is certainly larger than certain constant times phi minus its average in L2 to the square. Right. Okay, once you have this, you return to the linear Boltzmann equation. You multiply both sides of that linear Boltzmann equation by f. You integrate, you apply a green formula to take the boundary condition into account. And that essentially tells you that the entropy production is bounded below because of that bound. It's bounded below by something of this type, right? So you have sigma times mu times the L2 norm to the square of f sigma minus its average, which you integrate. I think it's, I should also integrate in y, right? So it's dz, it's not only dx, it's dz, right? So this is bounded. Bounded from above by the derivative in y of that entropy flux, or linear entropy flux, if you want. And if you integrate in y and you use the fact that f sigma is bounded, you see immediately that you have a control of f sigma minus its average in L2 norm. But this control tells you that this guy, f sigma minus its average, it's for the 1 over square root of sigma, right? Yeah, so let me skip that for the moment, right? So yeah, I mean, if you return to this estimate here, you see immediately that because this is controlled by, this is uniformly bounded, so you see immediately that this tells you that this L2 norm here is controlled by a constant over square root of sigma. So here I have a square, right? So the f sigma minus its average is controlled by the n infinity norm of the source term over square root of sigma. Yeah, so you need, so this tells you that f sigma minus its average minus macroscopic density is ordered 1 over square root of sigma, but in fact you need 1 over sigma, right? 1 over square root of sigma is not good enough. So in order to get 1 over sigma, you need to do similar estimate once again. So you write the boundary value problem for this g sigma function, which is f sigma minus something which satisfy the boundary condition, right? Something that's equal to the radiation entering the domain, so that you get 0 on the boundary, right? And so this new function g sigma satisfies the same Boltzmann equation as before, except that it has a source term, and on the boundary, the boundary data is equal to 0, right? So if you want, you have traded the non-zero boundary data for something which is on the right-hand side. But that thing which is on the right-hand side has a special structure. You see immediately that it's a function of z times omega. And this is fundamental because now if you apply the H theorem to g sigma here, then the omega grad f sigma can be estimated, can be controlled by sigma times the deviation of g sigma from its average. So here you see that with this estimate here, you can show that actually f sigma minus its average, or g sigma minus its average, is the same, are controlled by the s, the source term, But be careful, it's not the source term in L infinity. This time you need the derivatives because you need to control the grad f sigma, right? So here you need the s on the boundary to have bounded derivatives. Okay, so if you do this, then you fix this difficulty here in the sense that f sigma minus its average is going to be of order 1 over sigma, right? So there's a little subtlety which you have to take into account at this point. Okay, so as for the diffusion limits, then you can write the weak formulation of the boundary value problem for the test function, which you choose to be of this form. So the test function is a function of z plus something which is proportional to my function capital omega, which I remind you is the solution of this integral equation here. Right, so if you pick a test function of this form, and if you pass to the limits in the weak formulation as sigma tends to infinity, you'll see that you get an identity like this, which is going to be satisfied for all phi's, say for all phi sin infinity with compact support, and you recognize in this identity the variational formulation of this problem here, right? So you recognize that you have Laplacian of rho is equal to 0, and that you have precisely this boundary condition equal to S, right? And once you're here, then you obtain the fractional diffusion equation by the harmonic extension representation of square root of minus Laplacian, right? In this way. Good. So, and then you have to, you have some technicalities to prove that the traces converge, that the derivative of the trace converge, but that I will not discuss in detail. Let me finish with a few remarks on this problem. So here we have treated the case of a half space, right? And with a flat boundary. There's something that you can always do is treat the case of a smooth bounded domain of Rd plus 1, which we call Z. Now it's no longer upper half space. It has geometry in the boundary. But with the same notation as before, nz for the outward normal field. So now if you look at the same linear Boltzmann equation as before, for large sigma and the same boundary condition, my pointer is really fading, so, well, I hope it will last another 5 minutes. So here gamma minus is the part of the boundary times velocities, or directions, omegas for omega entering the domain, right? So here the Dirichlet condition F sigma, the number density of the particles entering the domain, is the sum, it's the superposition of S of x, which is scaled by something proportional to 1 over sigma, or asymptotically proportional to 1 over sigma, plus something which is of the form 1 minus 1 over sigma times the outgoing flux, right? Because omega dot nz positive is for outgoing particles. Then you can show by essentially the same techniques that Laplacian rho is equal to 0 and that you have this Robin boundary condition on the boundary. Now, if you denote by lambda the Dirichlet to Neumann operator on dz, you can replace this boundary condition here by an equation for the trace, for the restriction of rho to the boundary, which is going to satisfy this equation here. So you have R plus some constant, the same omega as before, whatever, times the Dirichlet to Neumann operator applied to R, which is equal to S. And this is the way the square root of the Laplacian appeared before, right? So this Dirichlet to Neumann operator, what do we know about it? So we know it's an operator that maps h1/2 of dz into h minus 1/2 of dz. So it has, so certainly square root of minus Laplacian in terms of counting derivatives fits in that picture, right? So it can be defined you can define it variationally by this formula here. And then you can compute it in a few examples. So the one that we've been using, this harmonic extension, is the fact that if Z is the upper half space, then indeed lambda is equal to the square root of the Laplacian, the Euclidean Laplacian on RD. Now if you take the unit disk in R2, then you can check with Fourier series that I think that lambda is the square root of minus Laplacian on the unit circle. Right? I mean, you extend Fourier series for those, you extend Fourier series going inside the domain. But as soon as you take the unit ball in RD, then you can check that lambda, of course, at high frequencies behaves like the square root of the Laplace-Beltrami operator, but there is some kind of shift which involves the d-1/2, which you encounter in spherical harmonics, I think, right? So you seem skeptical, this last formulation.
The square root, this is the Laplace on the sphere d-dimensional or the d-1-dimensional sphere?
Yeah, I'm sorry, d-1 is, in fact, everything in D is in d+1, actually.
Oh,
yeah. Yeah, so here it's, it's a d-1, yes. Sorry about that, okay. Okay. Good. So, so this is the first remark. Okay. So some further open questions. You might wonder whether there is an analog of this result for the linearized Boltzmann equation, which appears in the kinetic theory of gases. You take the Boltzmann equation written by Boltzmann and Maxwell, right? You linearize it, and is there something analogous to what I presented here? Well, first, there's something I didn't emphasize too much, but which is nevertheless important, which is here I've been using significantly the maximum principle, the fact that the linear Boltzmann equation satisfies the maximum principle, whereas the linearized Boltzmann equation does not, right? So linear Boltzmann equation is not, I mean the linearization of the Maxwellian of the Boltzmann equation is not an example of linear Boltzmann equation, the semantics, which is a little strange, right? So because in particular it does not satisfy the maximum principle. So in order to be able to do that for the linearized Boltzmann equation, first, mathematically, you need to get rid of the maximum principle in the argument, and that I don't quite know how to do at the moment, unless we can consider bounded domains, but we've seen that bounded domains, I mean, you have these examples to show you that in the end, you will almost never get exactly square root of minus Laplacian, except in the case of the unit disk, which is maybe too peculiar anyway, I don't know. There's another question, which is whether one can get powers of minus Laplacian other than square root of minus Laplacian, other than 1/2. That would require strong anisotropy in the diffusion limit for the linear Boltzmann equation. That's probably a bit, that would be a significant modification of the geometry of the scattering operator, so I don't know. Let me, however, say a few words about question A, which I've been investigating with my colleague, Professor Aoki from Kyoto, or presently from Tainan in Taiwan, from Tainan and Taipei in Taiwan. Right, so if you take the Boltzmann equation from the kinetic theory of gases and you linearize it about the Maxwell-Boltzmann distribution, say for simplicity, with pressure equal to 1 and temperature equal to 1, you do that in half space, where here my y is going to be x3 positive, and you assume that you have accommodation boundary condition at x3 equal to 0. The accommodation boundary condition is something that tells you that gas molecules impinging on the interface, there is a proportion 1 minus alpha of it that's reflected specularly on the interface. So VR is the velocity transformed from V by specular reflection on the interface, right? And then you have a term that looks like very much the Lambert reflection law, which goes by the name of diffuse reflection in the Boltzmann equation literature. And that's, so you take the flux of outgoing particles. Yeah, it's really, this one is really dead almost, right? So you take the flux of outgoing particles, and out of this, you construct a Maxwellian. This Maxwellian involves the temperature of the wall, right? And you re-emit particles with this law in the domain, in the upper half space, okay? Now, you assume, you start from the Boltzmann equation in this way. You assume that F is going to be a small perturbation of this equilibrium state M, right, 1, 0, 1. And accordingly, you assume that the temperature on the wall is a small fluctuation of temperature constant equal to 1. So it's almost at equilibrium with the gas, or more, I should say that the gas is almost at equilibrium with the boundary, which is probably more physically correct. And then you have, if you drop the nonlinear terms, you have a linearized Boltzmann equation, which looks very much like the one I presented before, except that it does not satisfy the maximum principle. And you have a term on the boundary where the density going in the half space is 1 minus alpha times the specularly reflected density plus something which looks very much like the Lambert reflection law, right? Well, the scaling here is quite surprising because, you know, here, so what plays the role of sigma is my 1 over the Knudsen number. So the Knudsen number is the ratio of the mean free path of gas molecules to the typical dimension of your domain, right? And here, you would assume that if everything was like in radiative transfer, you would assume that you need to take alpha close to 1, because this is the thing that looks very much like the Lambert reflection law. Yeah, not so. I mean, the appropriate scaling here is that alpha should be proportional to Knudsen, right? So if you take alpha close to 1, it's not going to work. And I tried endlessly doing computations with this, and of course, no avail. There is really a difference between the role of the temperature in this theory, in the Boltzmann equation of the kinetic theory of gases, and radiative transfer, and the radiative intensity and radiative transfer. There's really a difference between these two quantities. So the message here is that if you want to try this problem, then you should take alpha proportional to the Knudsen number. You should take alpha small and not alpha close to 1, right? But if you do this, then formally you can do some asymptotic expansions, which have been partially explored by Kazuo Aoki, Taku Inamuro, and Onishi already some time ago, 1979, long time ago. Right, and eventually you can prove that you arrive at Laplace equation for the fluctuation of temperature to leading order, with again Robin boundary condition for the temperature fluctuation on the wall, and this well, I mean, it's the temperature of the gas on the wall, right? So it's not the temperature of the interface, temperature of the gas on the wall, and so you can check that this temperature by the harmonic extension principle solves a fractional diffusion equation equivalent to the one which I presented in the case of the radiative pressure in radiative transfer, radiation pressure in radiative transfer. All right, with that I'll stop. And thank you for your attention.
Thank you. Do you have questions? So I hope, yeah, let's see.
Can you elaborate about your comment on the emergence of fractional powers of Laplace operator and isotropy and break of isotropy?
Yes. Okay. Yeah, it's a bit. Okay. All right. So you mean point B here? Yes. Okay. So you see. So in this business, the way you obtain the fractional diffusion equation is by establishing the Robin boundary condition on the boundary, right? And now if I go back to the Caffarelli-Sylvestre approach to the fractional Laplacian, you see that if you want that the normal derivative, if you want that the normal derivative to be a power of the minus Laplacian other than square root, then you need that the boundary, you need that the harmonic extension in that case, in other words, the diffusion equation in that case, in the domain, in the upper half space, you need it to be equal to this operator here, right? So if you want this to be given by this operator here, now if you look at, yes, if you look at the standard diffusion equation, the standard way you derive a diffusion approximation from linear Boltzmann equation, so you see that here the diffusion coefficient is 1 over d times sigma, right? And sigma is the scattering rate. Okay, so here, because sigma is a constant, it's outside the Laplacian, right? So, but typically it will be the divergence of 1 over d sigma, if sigma would depend on x or z or whatever. So it will be 1 over d sigma of z times the gradient of rho, right? So you see immediately that if you want that diffusion equation to be if you want that diffusion equation to be equal to that, then you have to modify the model. The model has to be such that the scattering rate, scattering mechanism somehow not only has to depend on the height in the half space, but also the function capital omega, which appears in the computation of the diffusion coefficient, has to mix y, it has to mix the height in the half space and the angle in a non-trivial manner, right? So I would assume that it's not, I would assume that you need a rather strong correlation between the scattering phenomenon and the height in the half space if you want to have a chance to obtain such a diffusion equation. Yeah, it's not so easy.
Thanks.
Other questions?
So you started with linear Boltzmann that is cut off. Have you tried with non-cut off?
I start with the linear Boltzmann equation,
which is in cut off. The scattering, the integral of the scattering is equal to 1.
Yes.
So have you tried the case that is non-cut off, where you have a fractional diffusion?
No, not at all, because I think it's quite unusual in radiative transfer. I don't know, actually.
Well, you have the highly peak regime, this Henniger-Grenstein.
No, I should say that I started with just the most standard models which you find in the book by Chandrasekhar. I have tried very, very basic phase functions, so I've not thought about such cases. But yeah, perhaps. So you mean that would change the yeah? I see. So so already from the outset you would have a non-local diffusion equation in omega, right? Yeah, somehow, right? In omega or v or whatnot, right? Okay. Yeah. So no, I've not tried that. I've not tried that. Yeah. Good point. Good. problem. Maybe difficult. Maybe too difficult.
Other questions? I do have a short one now.
Yeah.
In this fancy definition for the fractional power of the Laplace, I guess that when gamma is 1, you get exactly the Fourier multiplier modulus of psi.
Yes.
In that example with a flat boundary.
Yes.
But is it also true for different values of gamma that you get a Fourier multiplier, maybe in the flat case?
Oh, you mean for other values?
If I compare,
for other values of gamma, I have to solve this. You take Fourier transform in X,
yes.
and then you have to solve this.
Yes, and I guess you find indeed in the flat case.
Then you find a Hill equation.
Yes.
It's not so easy, right? No. So you find.
No, but I guess maybe I formulate my question in a slightly different way. I guess that if you take that picture and the boundary as curvature, then you get a definition, which does not use Fourier transform, of course.
Okay.
And my prognosis would be that definition would be easy to generalize to the curved case, whereas the Fourier definition would be limited to some kind of a flat case. This is a prognosis, but this is a question.
Yeah, but I'm not. I mean, you should really pick the brain of someone else.
They do that in geometry.
Yeah.
Yeah, they do that in geometry.
Yeah, sure. That's yes.
Okay, I mean.
But I'm sure that Kwasniewski should know this.
Okay.
The first speaker of the first day.
Okay, I don't think. Okay, thank you. Other questions? Well, thanks again.
Thank you.